In math class in school, in geometry, you learn about this relationship about the sides of a right angle triangle. And this relationship is incredibly important and really useful in a lot of fields. But to me, it was always weird that I never really understood why it happened. And this relationship, of course, is called Pythagorean Theorem. And it states that when you have a right angle triangle and you have these two sides, A and B, which connect at the right angle, there's a relationship between them and the hypotenuse, so the line that does not connect to the right triangle. And that relationship is the square of A plus the square of B is always equal to the square of C. So I have an activity that I believe it's one of the oldest proofs, and it may even be Pythagoras' proof himself, about why a squared plus b squared equals c squared. And I hope you enjoy it. Now, for this demonstration or proof, you're going to need a few things. First of all, you're going to need two pieces of paper that are cut into perfect squares and are actually totally identical. So when you put them on top of each other, you can't see the other one. They're completely lined up. And they don't need to be colored paper, but I think it makes it a little bit more visual. You're also going to need a ruler. You're also going to need a pencil, and you're also going to need a pair of scissors. So I'm going to start off with the blue piece of paper here. And so one of your pieces of paper, what you're going to need to do is choose a distance, how long you want to make the sides on your triangle. And I'm going to go along here and measure, say, 8.5 centimeters. And I put a little dot here. I would really encourage you to choose some other distance. And if you're doing this with a class, have everyone choose a different distance, just to show that it works for all sorts of different distances. And now, if you go around and you keep on measuring that exact same distance from the edge, then you will end up with a situation where you can draw some triangles. So I'm going to make a dot there, and you have to be really exact with this. The more precise you are, the better this will work. So now what you want to do is take your ruler, and you're going to go around and you're going to connect the dots on the adjacent sides. You don't want to do it across the center of the paper, but you're just going to connect the dots that are on the sides that are beside each other. So now what you're going to find that you have is a square. You can measure it with a protractor to see that the angle here is the same on every single angle, but it's 90 degrees on every angle. Or you could even use your knowledge of angles and figure out that it is always 90 degrees. And you've got these 4 identical triangles. And because you measured one side, then you'll know that that side is the same on every single triangle. And the side that you didn't measure was actually just what was left over, and since it was a square, all of these sides have to be the same. So all of those sides will be the same throughout the triangle, or throughout the triangles. Similarly, you'll know that all these lengths are the same as well. Again, you can measure them, or Pythagorean theorem will actually prove this. The next thing you need to do is cut these triangles out. So now I am left with 4 triangles that are all the exact same shape. No differences between them. So now I'm going to bring back the piece of orange paper. And the first thing I need to do is place all these triangles so that they make the same pattern that we had before. You do not need to flip any of the triangles over. They should just stay flat the way they are. Okay. Now, let's go ahead and label parts of these triangles. So, we are going to label this part on the bottom here, we're going to label as A. And then this part we're going to label as B. And then this part at the top will be C. Now, as you're quickly going to notice, the square in the center here has all sides that are length C. All sides are length C. So what we're going to do is we're going to actually draw that square in the center. Again, try to be as exact as you can with the placement of the triangles. And use your ruler to draw the lines. So now, what you want to do is look around and label, well, we know that the length of this line right here is going to be C. So let's label that C, because it's the same length of line as it is on the inside, so it's the same line. And then on this one here, we're going to call this one C, because it's also the exact same length, and here, and here. Okay. Now, we can take these squares away for right now. And we can see here that we have got a square with all sides length C. Well, we can calculate the area of a square. So area equals length times width. Well, in a square, all the lengths and widths are the same, so the length is C and the width is C. So we know that that would be C times C, which would be C squared. So we know that the area of this square right here is C squared. Now that we've figured that out, let's take our piece of paper and flip it upside down. So it's the exact same area of this square, but we can draw new things on this side. Now, if I start with my original triangle positions that I had up here, now I'm going to move these triangles a little bit. So I'm going to take this triangle and I'm going to just move it down here, like that. And I'm going to take this triangle and I'm going to actually turn this one this way and move this one up this way. And if you have done this really accurately, you're going to find that you end up with two rectangles. So let's again draw lines over these rectangles. And let's find the other rectangle and draw it as well. So we now have a situation where we have a rectangle here, a rectangle here, a square here, and a square here. Well, how do we know this is a square? Well, first of all, we could check that they are all right angles. Second of all, we can see that this side here has to be A, because it's the same as that one there. And this one here also has to be A, side length A. And if you wanted to, you could continue this up and see that that is also side A, and this one is also side A. Similarly, down at in this square here, we can see that this is side B and side B. Now, again, I'm going to move these out of the way, fix my line up here. So, I have two squares, and I know that this one, using the same logic from last time, has to be A, which is the length, and A times A, because they're both the lengths of this square. So in this case, A times A is going to be A squared. And down here, the side lengths are both B, or all B, I should say. So if the length were to be B and the width were to be B, it would be B times B, which is B squared. I decided to make one little change to my video. I added this line in here and this line in here just to demonstrate that those are in fact two triangles. And as we know, those triangles are the exact same area. And just like that, these two are also two triangles that have the exact same area. All four have the exact same area. So what you can see here is that we don't really care what the area of these triangles are as long as they're the exact same. But you can see that the area of the four triangles here plus the area of this square, which we know is A squared, and the area of this square here, which we know is B squared, gives us our full orange square, the full total area. And if I flip that paper over, we know that our area is the same as the area of the four triangles, which haven't changed, plus this C squared. So let's put that down in writing. Now I'm going to wrap this video up with a little bit of algebra. To do that, I need to define a couple of terms. So first of all, my A total is going to be the total area of all the shapes combined. So in the example I was showing, that's the large orange square that I was using. Also, A four triangles is the area of the four triangles. In my case, they were the blue triangles. And with both of these, the total area and the area of the four triangles, they don't change between the two examples that we looked at. So what expressions can I write for those two examples? Well, in my first example, the total area was equal to C squared plus the area of the four triangles. And we can look at that right here. So my area was C squared plus the area of the four triangles. Now, in my second example, the total area was equal to A squared plus B squared plus the area of the four triangles. and that was demonstrated here. So again, we had a squared plus b squared plus the area of the four triangles. Now, as you'll notice, both of these expressions here are equal to a total, and a total has not changed. So, if this is equal to a total and this is equal to a total, then these two expressions must be equal to each other. So I'm going to rewrite this to c squared plus a four triangles is equal to a squared plus b squared plus the area of the four triangles. Okay, now what we're going to do is we're going to look at these two sides and see what can we get rid of. Well, this area of the four triangles is on both sides, so we can subtract. As long as we do the same thing to both sides, we are allowed to subtract numbers. So if we take away the area of the four triangles from both sides of the equal sign, then they will simply cancel. And we're going to be left with c squared equals a squared plus b squared. And since it doesn't matter which side of the equal sign these are on, because they're equal to each other, we could rewrite that as a squared plus b squared equals c squared. And there you have the Pythagorean theorem. I created this video to hopefully give people a better understanding of Pythagorean theorem and why it works. And to do that, it's important to try to, instead of just thinking about a single triangle, imagine it as this relationship between four triangles and two squares. And if you think about it that way, one thing that you can start with is, this was my initial example of what I did, but if I had have done it where the distance of A and B were actually the same, then I would get the smallest possible square, blue square, inside this orange square that I could get. And the more that I move that, so the smaller that A got and the larger that B got, the larger this square would have to get. As you can see, my square is no longer big enough to touch the outside edges, whereas when it was in the middle, they were all actually going outside the outside edges. And as I keep going and keep going, you can imagine the relationship. B is going to get bigger as A gets smaller at the same rate, because those two added together have to give you this edge. But this C is changing at a different rate. That's why it's no longer touching the edge. And you can imagine, as you continue to keep going, and this A gets closer and closer to being 0, this square, this blue square in the middle, is actually going to keep getting bigger until the point when it's actually the exact same as this orange square. And that point is going to be when you no longer have a triangle, when A becomes 0. So if A becomes 0, then B is going to be the full length of this side, and this blue triangle, or this blue square, is going to be the entire size of the orange square. And in that case, you would have B squared would be the entire size of the orange square, and C squared would be the exact same size square in the blue square, and A wouldn't exist, and you'd be left with a line. So A squared equals 0 plus B squared, which would be the full size of the square, or the full size of this line, I should say, is going to give you C squared, which is also the full size of this line, and C squared being the full area of this square. So I'm hoping that you see that this relationship continues along the entire length of this object. I hope this helps you, and good luck with using Pythagorean theorem.